In addition to the spacewalk work that they performed on the outside of the station, obviously with some maintenance tasks, there's also a number of experiments that are being carried out external to the space station in addition to all the work inside the station. There are numerous free-flying satellites that orbit the Earth and map our planet for various areas of research. And of course, we now have a new payload that's been installed on the International Space Station's external segment to give a different perspective. Lori Meggs is at NASA's Payload Operations Integration Center at the Marshall Space Flight Center in Huntsville, Alabama, to tell us more about it. Lori.
RapidScat is an instrument that will be used to measure wind speed and direction of the oceans, and it will begin a new series of mounted satellites on the ISS for weather monitoring. I recently spoke with Stephen Voles. He is NASA's Associate Director for Flight Programs, to find out more about what this new satellite adds to the mix.
But what we're seeing with the launch of RapidScat is the first Earth Science Division, Earth Science focused measurement that NASA, I think, is invested in. That is built for and adapted to the ISS specifically. It's an active radar system. It sends microwave radiation down, it transmits it down, and if you have a picture you'll see this. It's a rotating dish. It transmits a pulse down. It's about 100 watts, which is not, it's a light bulb. And then it bounces off the surface of the ocean, that radar. Now the ocean is rough or smooth depending on how much wind there is above the ocean. So a rough surface gives you a different scattering, and we've done a lot of research over the past 20 years to understand, to measure the scattering of the ocean tells you the amount of wind right above the ocean. That's why it's ocean winds. It doesn't work over the land because obviously the land doesn't scatter, doesn't get reflected. So these are ocean only. But by looking at the reflected signal, and there's the antenna just picks up that signal and records it, you can tell the surface roughness of the ocean, and that can be immediately transferred into a measurement of the wind speed, the wind velocity at that spot. So it gives you the wind velocity in every spot you look at.
So what do we learn from this new RapidScat system?
What RapidScat does, and is emblematic of what the ISS does in general, it provides some of the same measurements that we have from QuickScat, which is another scatterometer, but it actually does it from using the ISS as a platform. It does it in a different way, which is quite unique and actually very complementary to the free-flying satellites. What RapidScat does, it has a rotating antenna which measures vector winds, ocean winds, over a fairly wide swath, several hundred kilometers. But it gives us a rapid repeat and a high visibility of those areas, the tropics regions, where we have the most tropical storms. What it also has is it was built with the same hardware that was used for QuickScat, or QuickScatterometer, which was launched in '99. It has the same accuracy, the same spectral resolution, the same measurement technique, which was used then, so that data record that was started in 1999 is picked up by RapidScat, ISS RapidScat, and then can be continued forward. And it's one of the key features of Earth system science is we're looking for decadal science. We're looking at things that vary very minutely over decades. So to do that, to understand that, you have to have a constant and consistent data record. RapidScat will anchor the 11 or the 14-year record from QuickScat and carry that forward into the next, to the next satellites and be cross-calibrating then with ASCAT. Now what ISS does, which is really kind of cool and useful for us as a tool in the measurement, is it's in what we call a precessing orbit, which means it doesn't cross the same spot on the Earth at the same time of day. It varies as the day rolls by, so sometimes it'll cross over Kennedy Space Center here at 6 a.m., sometimes noon, 1 p.m., etc., every hour of the day over a period of time. Winds are highly variable, and sometimes they vary on a day-to-day basis, hour-to-hour basis, and by viewing the winds globally at various times of the day, you get to see what's called the diurnal cycle, a diurnal variability. Now you'll notice here it's windy in the morning, but it's calm at noon, and then it's windy in the evening. If you only take measurements at noon, you think it's always calm, there's never any wind, no persistent winds. By doing it in multiple times, which is what ISS enables, you get to see that variability over the day, and that strongly complements the single crossing time measurements that we have from our polar satellites.
So what do we use this information for? When we get the data, what is it used for?
There's a weather application and there's a climate application. The weather application is the output from QuickScat and from RapidScat in the future goes directly into improving the numerical weather models that NOAA uses, that EUMETSAT uses to understand the intensity of hurricanes, for example, when they occur, or just weather in general. So there are inputs that we've been providing to the weather services for the last decade with our scatterometers, which this will continue and add to. So that's the weather purposes, which is very, very important and improves the value of our predictions. from a climate point of view, what it does is it allows the variability, the diurnal variability, allows us to look at a different aspect of weather, of wind variability over a day that we don't have with our existing orbiting satellites. So that's going to open up new avenues of investigation and understanding of how the wind cycles change in particular spots on a daily or hourly basis. And it's a whole area of research that we have spot data from airborne science, et cetera, but from a satellite perspective, we don't have a good, consistent data record to start looking at. I think it'll open up new research areas.
And RapidScat engineers tell me this morning that the data is coming down looking great, and they're still undergoing calibration, but a successful start to a payload that should be on the space station for at least 2 years. Taking a live look into the Payload Operations Integration Center right now, we have TJ Creamer, the Payload Operations Director, leading the team here today, and he knows a little thing or two about being on space station and running those experiments himself as an astronaut. And also the PACOM, I want to point out JP Wilson. He just certified this week to become a PACOM, and that is the payload communicator who speaks with the astronauts and helps them with all of the experiments that they are participating in on orbit. And that will do it for us from the Payload Operations Integration Center at NASA's Marshall Space Flight Center. Now back to you at Mission Control in Houston.